Okay, what do we call this? The factored form of an equation. Okay, this is now there's nothing special about that name, except it's going to be in instructions sometimes. Okay. Now, so this is the factored form. This is what was an equation that started at ax some power, well, what power? 1, 2, 3, 4, ax to the fourth plus bx to the third plus cx to the second, and so on, going downwards. And at some point, figure out how to take it the other direction. We actually, right now, might be a good time before we actually start this problem. So, if the instruction said, what is the original? Well, in that case, probably the first thing I do is I would do this term. And that term is going to give me x squared minus 2x plus 1. Right? I've still got the x out front, and I still got the x plus 3 here. Next thing I would do is I would distribute here, 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 and there, there, there. In other words, multiply that x plus 3. So I now have x times, well, what does this business all come out to be? X squared times x is x to the fourth. Negative 2x times x is negative 2x squared. 1 times x is x. Now these, 3 times x squared is 3x squared. I'm lining up my powers. 3 times negative 2x is negative 6x. And 3 times 1 is 3. I'll expand that. So this simplifies to x to the, well, here's my x. And I've got x to the fourth plus x squared minus 5x plus 3. Yes. Yes, yes, thank you. I mentally already multiplied that one. Thanks for catching that. Okay. And this also should have been an x cubed here. Okay. Now, I've got to distribute this x. So when I do that, I end up with y equals x fourth plus x cubed minus 5x squared plus 3x, and no y-intercept shown, which means that the y-intercept is 0. Okay. Right here, this tells me x is 0, that point right there. So that shows us that the y-intercept is 0. Okay. Now, this gives us x equals 0. This gives us x equals negative 1 with multiplicity 2. So this is a touch and go. This is a crossing. This one gives us x equals negative 3. And this one is a crossing because of the rules of multiplicities. Remember, there's a hidden 1 here. So if the power is odd, it's crossing. If the power is even, it's touch and go. Okay, our turning point, if you please. I could put TP instead of TG. Anybody ever done a TP party? No, we don't want to. Well, anyway, here's the graph of this. Here's the -3, here's the 0, here's the 1. You see, this is indeed a crossing point. This one is a touch and go rather. This one is a crossing, and this one is a crossing. This being a 4th degree equation, it's got to end up and up. Okay, that's a 4th degree equation. Any questions about this one? Any questions about how to find the original equation? Now, there's going to be stuff a little later about if the number in front of that x is something different than 1. That makes it slightly more complicated. Okay, this one is kind of similar. We've still got a y-intercept of 0. We've still got a value of +1, and we've still got a value of -3. The only difference is they've changed the multiplicities of 2 from this one to that one. That's the only difference in this and the last problem. Is now the power of 2 is over here instead of up there in the last problem. We have to take x plus 3 times x plus 3, that times x minus 1, and then that times x, if it asks for the original equation. Okay, but it doesn't, so we're not going to do it this time. Again, 0, -1, or +1 rather, and -3. This one has to be a touch and go this time because it's a even multiplicity. This one is an odd, so it is crossing. That one is also an odd multiplicity, so it is crossing. Okay. How would you find this maximum right here? Well, 1, 2, 3. I try about right here. In other words, I try about -1.5 on an XY table. Okay. Likewise, same way, I try 0.5 or 1/2 to see how deep this went. If you needed to be really accurate. In this one, you don't. Questions before I go on? Anyone not ready yet? Shelby, you look like you're not sure.
Me?
Yeah.
Oh, I'm good.
You're Shelby, right?
No,
No, wrong name. What is your name?
Emily.
Emily. Sorry.
Yes.
Okay, sorry. I would just quit guessing names because I have about a 90% fail. Okay, well, there's your touch and go stuff. What about this one? What total degree do we have? Now, we've got a -a term. What does that mean for us? Well, if it's even, that means it's going to be down and down. If it's an odd total degree, then it'll be up to down instead of down to up. So let's count our powers. 2, 3, 6. So it's a total power of 6. So that means it's got to either be up and up or down and down, and that negative first term is going to make it go down and down. So that's going to be our general direction. This is going to give us an x value of 0. Okay. That gives you a value of x is 0, but it is a multiplicity of 2. So this time that 0, which also happens to be the y-intercept, is going to be a touch and go either this way or that way. We'll have to look at the ends before we can tell. So that one gives us a -4, and it's a 1 degree, so it's a crossing. The next one gives us a 7, and it also will be a crossing. Oh, well, let's graph it since they did graph paper. Here's the x equals 0. Here's the x equals -4. Here's the x equals +7. We said that its end values have to be like that because it's negative. So that means that these two have to go that way. Now, this -4 happens to be a crossing. This one happens to be a touch and go. And this one happens to be a crossing. So what that means is this one has to cross above, go some amount of high, touch, change directions, go back this way, and then back down there. Kind of a golden arches. Okay? Anyone not sure about what I just said and how I drew that? Okay. Here we're talking about the term relative minimum and relative maximum. Now, there is a rule that if you consider the highest degree of the equation, you can have one less turning points. What does that mean? If I have 1, 2, 3, 4, 5 points on the axis. Okay. Let's just, 5 points would be this type of a graph, right? Assuming it's a positive leading term. That means this thing's gonna end up going like that. Okay. Now, how many turning points did I have? I was going this way and I turned. Then I was going this way and I turned. And then I was going this way and I turned. And I was going this way and I turned. What this rule is saying is if you consider the highest degree of the equation, which in this case was 5th degree, okay, that didn't show up very well. Left my lid off too long. Okay, if this is a 5th degree, at most, I can have one less turning points than I have degrees. That's all that says. Now, does it mean I have to have one less? No, I could have fewer, but I could have maximum one less. Okay. Like I could have 2 or 3 or whatever. You know, if I had some crossing point things in here, then it would be a little different. Let's say this one were a crossing point. Then it might go like this. And in this case, I would have 1, 2, 3, 4, 5, 6. Except that would, if those were crossing points, I would have to have this be a 7th degree. So anyway, that's it. you can at most have one less turning point than you can have degrees. Not a real big deal. Here's just an illustration of that. Degree is 3. If you graph this thing, it looks like that. You got one less or 2 turning points. That's all that they're saying in this one. Okay. Here's a set of rules. Whoops, too fast. For graphing polynomials. Now, we've been doing it. This is just a recap of what we've already been doing. Okay, so let's think of what we've been doing. We look at the leading term and the power to determine the ending points. Both up, both down, one up, one down, you know, that sort of thing. What's the next thing we do? We try to find the y-intercept. How do we find the y-intercept? Replace x with 0, which wipes out everything except the last number. Okay? Determine the multiplicities. So we know whether it's crossing points or turning points. And then we plot these points and sketch it. Okay. This determined field 0 is where we find the x points on the axis. I may not have said that out right. But that's generally what, I mean, it's exactly what we've been doing. So it's just a recap. Well, anyway, draw a sketch beginning at the left end behavior, put the right end behavior, and then figure whether they cross or touch. Okay. Now, this last one is just saying make an XY table if you need to figure out exactly how high or how low those maximums or minimums go. Okay, what about this one? If we want to sketch it, leading term is going to be positive, total degree is 2, 3, 4. So we're looking at this. Okay, so our general shape, this. How many turns are we going to have in this? 1, 2, 3. Total degree, that, at most 3 turns. Okay, they're finding the y-intercept here by replacing x with 0. They put 0 there, there, and there. So you get -1 squared times 3 times -4. Okay, and that gives you -12 for the y-intercept right here. Now, if we had a bare bones x out here, or x squared, or whatever power, then we wouldn't have to do this because we'd already know that it was the y-intercept was 0. So anyway, we're going to graph the point 0, -12, somewhere way down here. Okay. Now, based on that thing, we need to find our x values and whether they are touching or crossing. And that's what that is. So we've got an x equals 1. We've got a touch and go at x equals -3. We've got a cross at +4. We've got a cross. Now, we said our ending values are this. So we draw the 2 ends. we know this one's a touch and go. This one's got to continue below. And at some point, specifically way down here, it's actually probably going to go more like this. And that's a touch and go. So it's going to come back down and up like this. Now, do I know exactly how deep this goes? No. Do I know exactly how deep this goes? No. But this is a sketch, which is what they asked for. Okay. Would be looking for on a test. Questions about? Okay, here are the x-intercepts based on that. Okay, here they're gonna say find the approximate maximums and minimums, okay? For this particular. Kind of ignore that right there, but look at this. If we wanted to know how far down these go, how far up they go, pick a point between 3 and 1, -2, right here. They substituted -2 into all of those for x and got -63, which would be way the heck down here somewhere. I assume these go by tens. Okay. In this case, they chose 3 being between 1 and 4. Okay. They substituted it in and got -24. 1, 2, and a little more at 3. Okay. I guess I didn't do 63 right. But anyway, you got the idea how that works. On this one, you do this one. They were determining the total power and the n values, or the n shapes. There'll be at most 2 turns. So in other words, this thing, it's got to start high and low because there are two turns. It's probably going to look like this. Because there are two turns at most, at most. Okay, we find the y-intercept by replacing x with 0. Okay. Which would be down here. Okay. On the same problem. I've got x values of -1 and +3. So the x-intercepts are that. This -1 is a crossing, that is a touch and go. So here is my -1. Here is my +3. Here is my y-intercept at -9. We had it on the previous slide. -9 we had on the previous slide. We know this one happens to be a crossing. We know that one has to be a touch and go. So there's our shape. What if you got an equation in this format? Highest degree is still 3. Okay. Still a negative, so we're still going to go high to low. This is not the same equation as the previous one. Okay. If we factor this, we can factor out that -x. So that tells us the y-intercept is 0 without having to do calculations. We've got, now we factor this. That's a conjugate, so x minus 2, x plus 2. So that gives me plus or negative, plus or minus 2 for my x values. What do we know about multiplicities? First multiplicity, first multiplicity, first multiplicity. So they are all crossing. So if here are our ending values, this orange, then our connective values are keep crossing and keep crossing. Okay, we do have a minimum right here. We do have a maximum right there. Okay. Here's where I tried to find out how far down they need to go. If that right there is -2, I tried -1 as a substitute for x in the equation, and I got -3. So that's my minimum there. The minimum of -3 at x equals -1. For the other one, I tried +1, which was about halfway between. Substituted it in, I got 5. So then my maximum here is y is 5 when x equals -1. Notice my wording for maximum and minimum. Y is 5 when x is +1. Or whatever I said it was, yeah. Okay. So I have a maximum at y equals 5 when x equals -1. Again, watch that wording. Okay, questions on this slide? Okay. Now, this one, we're going just the opposite. Okay. Here, I give you this, and I tell you, find the polynomial. All I'm doing, these are the x values here. And you got to find that. Now, how do you do it? Well, if x is 2, -2, and 3, then that produces 2, -2, and 3. Then that produces these factors. Remember, the solution and the factor are always opposite sign because of that zero products rule. Okay, so that gives me these 3 factors. They happen to be crossing. For the sake of graphing it, that becomes important. And we've got this shape. Now, to find the polynomial, we take the pair of these, which are a conjugate right there, x squared minus 4, and then we multiply it times this one by distribution, get that, and simplifies down to this. This is the polynomial. Find the polynomial given only the zeros are the roots. Okay, you will be tested on that. You'll be tested where I give you the zeros. You'll be tested where I give you the factors. Okay. You may be tested where I give you this. You have to factor it and find the zeros. Okay. So all those possibilities are things that you're going to have to be able to do. And in this case, the y-intercept happens to be 0, 12. Simply by replacing the x's with zeros. Or you could look at just right there on the multiple. Second one, well, we've got a crossing, and a crossing. In this case, the zeros are the zeros. These are the factors here, are the zeros. We plot them. Third degree, low to high, because everything's positive x's, and multiply it out, and this is what you get. The fact that there is no number on the end verifies the fact that you've got a y-intercept of 0. We got a nasty one. These are the zeros. Those are not the factors. So, remember, if you have a square root, you also have its conjugate. If you have an imaginary, you also have its conjugate. A plus or minus bi, kind of a thing. Okay? So, this means that is actually 2 separate roots. X plus, opposite sign, radical 3, and x minus, radical 3. Remember, opposite sign when you go from 0 to our roots to factors. And then this one is going to be a -2. So that gives us our factors. It's real easy to forget that this generates 2. Okay. What if I had just told you the minus one? Well, if I had just told you the minus one, you've got to know that there is a positive that's got to go with it. Okay? And you're going to be tested like that. On the final, expect to have a problem, kind of like this one, where it'll tell you, but it'll just tell you one square root. And you've got to know to do the plus or minus. Now, it could be 1i, and you've got to know there has to be a plus or minus I. Okay, and we'll deal with that one down here. So anyway, we got these 3 factors. We multiply those 2 together. Square root of 3 squared is just 3, so that becomes easy. Then I have to multiply it times the x minus 2, and simplified, I get this thing. Okay, here's my y-intercept. My degree is 3, a positive 3, so it's going to go like this. I've got 1.732, 1.732, and 2 for my intercepts, my x values. Okay, if you have to take square root of 3 to figure that out, so be it, but that one's one you might need to know. So anyway, they're all crossing. So it goes up here to the y-intercept, comes back down, keeps going down. We don't know how far unless we do an XY table. And this just wants you to generally sketch it, so don't worry about how deep it goes. Okay. I'm more interested in the general path. This one. This involves your handout 13. This one involves your handout 13. Or 14, whichever one that's handwritten of 13 and 14. What? 13, okay. Yeah, the handwritten one. Basically, we're going to use the process here that they used on that handout 13. Now, there's one point of this that's really a kind of a stickler point. Okay. Well, this one actually, handout 13 is a step beyond this. I'll have to show you it separately. Okay. Here we go. Anyway, they tell you you got zeros or roots of -3, 2, and plus or minus. Put that plus or minus there. They don't, you've got to know that it is there. Okay? And that will produce 2 separate roots. So this one gives me positive x plus 3. This one gives me x minus 2. The positive side of this gives me x minus I. The negative side of this gives me x plus I. Always opposite sign business, right? Because we're taking it to the other side. So we got these 3. Those 2 I multiply together first because they're conjugates and they're easy. Well, I squared is -1, so that means this whole thing, x squared plus 1 eventually. These 2 multiplied together come out to be that. And I simplify it. So here I end up with the answer of these 2 times the answer of those 2. So I take x squared times both, and I take 1 times both, and I get, here's the x squared, those first 3, and here's the times 1, the last 3. And I combine like terms, and I end up with this 4th degree equation. Okay. Based on that equation, I have a y-intercept down here of -6. So now I have 3 points I can graph. I can graph -3, I can graph +2, and I can graph the y-intercept -6. But I can't graph those 2. Because you can't graph or measure imaginary because it's infinite. Now, we look at this thing, and in all likelihood, it's going to take a turn like this. Why do I guess it's going to go this way? If this is a 4th degree, I could have 3 terms, right? 1, 2, 3 terms. That's why I logically drew it this way. Now, in what reality? Those 2 imaginary points represent somewhere on this little loop right here the imaginary x values if the x-axis were shifted, but we can't measure that. The only way we can find exactly how this thing's gonna perform between 3 and 1 and 0 is to do an XY table. That's the only way to be absolutely certain. Okay? I didn't talk about ending values, but they're basically up and up because of that degree. Okay, anyone not ready for me to turn yet? I'm gonna skip over this one. That thing, you can see you got 1, 2, 3, 4 degrees, so up and up in this case. And you've got a touch no point right here. That's the only thing that I want to talk about that. Now, I need to find a clean piece of paper. That's clean enough. So I can do a problem like handout 13 and go through it. Now, I'm going to make up a problem, and we could come up with an absolutely horrible answer, because I'm just going to make it up. Okay? Let's say that you have X values of 2, let's say -2, 0, and 3 plus 4i. Okay. Now, graph-wise, we know we've got -2, we know we got 0. That's all we know so far. Okay. Now, looking at this thing, I have factors of x plus 2, x, although I really don't know the degree of that. Okay. If that's a first degree, then we can go from there. And what's this? X minus 3 plus 4i and x minus 3 minus 4i. Now, remember, this has to be a plus or minus like that. It didn't show it in the problem, but you gotta know it. Okay? Now, why are both of these minuses here? Well, if I take x equals 3 plus 4i, and collectively, I'm going to put a parentheses around that, I take it to the other side, then I get x minus 3 plus 4i equals 0. Likewise, if this were a minus to start with, then I would get x minus 3 minus 4i equals 0. Okay, so if this is plus or minus, we've got those two terms. Now, it's easier to work if you'll use brackets instead of big parentheses. Okay, if you got them opening, you got to close them. Now, this will always give you that kind of a term. Always. Now let's deal with this. We've got these. I need a closing parentheses on that. Okay, so I got to multiply some stuff together. So let's multiply these two together, which is what handout 13 is about. instead of doing it the way it shows you on handout 14, which depends on isolating this plus and minus here, and then trying to use the conjugate rule, it's easier, less likely to make a mistake if you'll just distribute this negative and distribute that negative and make this into x minus 3 minus 4i and make this into x minus 3 plus 4i like that. Now I'll just bring these two down. Okay. This one in front. These two I can solve by distribution. It's a 3 by 3. X times x is x squared. X times negative 3 is negative 3x. X times negative 4i is negative 4xi. Okay? So that's multiplying by the x. Multiplying by the negative 3. I get negative 3x. I get negative 9, or positive 9 rather. And I get positive 12i. Multiplying by this one, I get 4xi, positive 4xi. Here I get negative 12i. And here I get negative 16i squared. And don't forget the square. So let's add all of this up. X squared. Okay. Here I get minus 6x. Those two nicely cancel. These two nicely cancel. Plus 9 minus 16 times negative 1. Well, that makes this into positive 16. So 9 plus 16 then is 25. So this whole thing becomes that. Okay. You follow me on how to do this? Now we got to multiply by these two. X plus 2 and x. Well, let's multiply by the x first. So I get x cubed. I get negative 6x squared. And I get 25x. Now I'm going to multiply by the 2. I get 2x squared. And I get minus 12x. And I get 50. Okay. So if I add this stuff together, I get x cubed minus 4x squared plus 13x plus 50. And now I have to multiply that by this x. Which ultimately gives me, I'm going to bring it over here, x to the fourth minus x cubed plus 13x squared plus 50x. And that would be the equation. Lots of work. Lots of work. Okay. Lots of steps. The most important thing to remember, though, is this business right here. How this produces those two terms, or this produces those two with both the leading negative. Okay, that's the biggest key on that one. Okay, you've got the handout you can look at later if you need to. Okay, very similar to this. Actually, my numbers on this one didn't turn out quite as horrible as I worried. We could have looked at this thing from the very beginning. Because this has to be both the plus and the minus, we knew we had degree 4 equation. Therefore, this has to be a degree 1x here. It goes 2, 3, 4. Okay, for the sake of graphing. And our y-intercept is 0. Okay. Any questions about this before we go on? That multiplying out factors of imaginaries is not a fun process. Okay, we're going to move on to something else, totally different. Okay, well, not, it's kind of totally different. Write down these 4 steps right here. Now, how many of you really enjoyed 5th, 6th, 7th, and 8th grade long division problems? Stuff like that. No fun at all, right? Let's see what they did in these problems when you were in, let's say, 6th grade. Okay. Now, 24 needs to go into 2 digits here before you put your first term, right? 2 digits, 2 digits, over. We're not even going to worry about a decimal in this. Okay. Now, in this case, the first thing you had to do is you had to play the Gazinta game. How many of you remember the Gazinta game? How many even know what the Gazinta game is? You don't? How many times this goes into that? That's your estimate step, the Gazinta game. This goes into that. Okay, yeah, another bad joke answer. Well, how do we figure out how many times this goes into that? Count your fingers. 24, okay, is almost 25, which is an easy number to count by, right? What are the multiples of 25? 25, 50, 75, 100, right? 100's too big, 75 a little bit too little, but that's okay. So that's why our estimate is 3. Okay, so what if this had been 27? Then I'd probably estimate with 30s. 30, 60, 90. Okay. All right, now, what if it was a 1? I'd probably estimate with 2s. Or 20s rather. Okay. Now, 3 times 24 is 72. There's my multiplication step. What do we do next? We subtract it. And we bring down. And then we just start over again. Now, when we do this, this has to be littler than that to get a green light. And likewise, when we bring down and we estimate and multiply and stuff, again, we've got to have littler and the remainder of 12 here had to be less than that to get a green light and go on. Well, anyway, we got the 72, we subtracted, we got 12, and we brought down this 5. Now we do the Gazenta game all over again. 25, 50, 75, 100, 125. Probably goes 5 times. Now, when I do this estimating game, you could be off plus or minus 1, but it'll get you close, is what I'm saying. All right, so anyway, we did the 5. 5 times 24 is 120. This is smaller than that, so we're good. We subtract, this is smaller than that, so we're good. And we bring down again. Okay, so we do the Gazenta game again, and we try a 2. We multiply, we get 48. We subtract, we get, and we bring down, we get 102. We do the Gazenta 4 times this time, 6 remainder. Now, when we started off in grade school, and we got that, we started remainder 2 in 3rd or 4th grade. Okay, about 5th or 6th or 7th grade, instead of saying remainder 2, we instead would say and 2/5, meaning the remainder over the divisor. Okay, now that's relevant to what we're just about to do. Okay. Oh, by the way, see this problem right here? I've got a missing term in it. I've got a missing x squared. Before you can do the long division that we're about to do, you have to put in that missing square term, because you've got to have all of the powers starting with your highest. This is kind of like if you write out in words 3048, we don't write out 3000 or 3048. We just write 3048, but we understand that there is a placeholder 0 there. Okay. And we will have to do that in some cases. This particular problem, what this means is we're actually going to divide that by this. Okay. Now, the bottom line is this is a form of factoring. This is a form of factoring for higher power problems, powers higher than 2. Okay. What we are speculating in this problem is that 2x minus 5 is a factor of that equation. Now, we'll know whether it is or not, depending on our remainder we get down here at the end. If we get a 0 remainder, then that really is a factor. And we've partially factored that equation with the answer we get up here. If the remainder is anything else besides 0, we don't. But that remainder on the end becomes a y value in an xy table. Okay, so let's do this division. I like to put a parentheses around this. If you remember, my multiply step said distribution, didn't it? So we've got to, when we do our estimate times this, we've got to distribute times both of them. 2 digits, 2 digits. Here's the first digit of my answer. Okay. I do the gazenta game. Right here is my estimating tool. That first number, that x value. Okay. What we do is we see what do we have to do to this to get that first term. Compare this and this. What do we have to do to this one to make it into that one? Well, we have to multiply it by x squared. So if I take x squared times 2x, and then x squared times -5, I'm going to get 2x cubed minus 5x squared. Ignore this line and that line for the moment. You get positive 2x cubed minus 5x squared by distribution. Now, the next step, the subtraction step. What did my list down here say? Change the signs and then add. Well, after I change the sign of this, these two cancel out, and that will always happen. If it doesn't, you got something wrong. These two, -11x squared and positive 5x squared, gives me -6x squared, and then I bring down. You see, this process is just like 5th grade arithmetic. Well, I estimate again. What do I have to do to this to get into that? I have to multiply it by -3x, don't I? So there we go. And by the way, you notice all my column powers perfectly line up when you do this right. Okay. So I take this -3x and I multiply it times both of those. And I get these original signs. 6x squared plus 15x. When I distribute, I change both signs. That's supposed to be a negative right there. I don't know where that little tail on the front of it came from. And these two cancel like they're supposed to. 13x minus 15x gives me -2x. And I bring down. Okay. I estimate one more time. This time, all I have to do is multiply by -1. So I do that. Change both signs and add. And in this case, I got a 10 remainder. Now, that 10 remainder tells me that that is not a true factor of that equation. Okay. It does tell me that somewhere on the graph that on an XY table, that 2.5 matches up with 10 there. It does tell me that. That's called the remainder theorem. Okay. So even though this isn't a factor, you still get a little bit of useful information, because this is a point on your graph that you can graph with. 2.5. Okay. Now, that's the process for this. We don't show it remainder 10. Here is how we show our remainder. Remember later on I showed you that 2/5 for the remainder on the 3rd grade problem or 5th grade problem. Now we're showing it this, the remainder over the original divisor. Okay. We've got missing degrees. So the first thing we have to do on this one is we have to put in those missing degrees. Now I'm going to jump through this because division is going to be exactly the same. We got a remainder, that's not a factor of this. Okay. This one, you're not going to have one of those. At one time I had it on my test when I'm not going to make you divide by 3 digits. It's just more complicated. Your first digit of your answer is 3 spaces over instead of 2. Okay, I'm going to run through that. Okay, I would like, if you would, to let me show you one more problem for the sake of Alex. We got this division problem, except now we're going to work it with what we call synthetic division. Okay, synthetic division. In synthetic division, first we got to look at we got missing powers. We don't. Powers you got to put in those 0 terms. Now, we only write down the coefficients, the numbers that are in front of the x's. Okay. Instead of writing the factor, we write the solution. Remember when you compare factor and solution, they're always opposite sign. This one uses solution. Long division uses factors. Long division was a subtractive. This is an additive process. Now, here's how you work this thing. Okay, here it is just written out. First thing I'm going to do is I'm just going to bring down that 1. Second thing I'm going to do is I'm going to take this times that to get my number here, which in this case would just simply be positive 8. Okay. So I multiply those. Now, the next thing that I do is I'm going to add these two instead of subtract. Okay. Well, that gives me -5. And then I start all over again. I take this 8 times that -5 to get my next number, which is 40. I add those and I get 6. Now I'm going to take that 8 times that 6 and get my remainder possibility. Gives me 48. I've got a remainder of 1. Here again, my end result here is not a perfect factor. But let's see what this end result is. Okay, I just shifted it up a ways, is all I did right now. Okay, there's the remainder. This becomes x squared. If you remember original problem, this was x cubed, this was x, and that was my C term. Okay? Excuse me, x squared. and X, and that was my C term. Original. Now, we're down here. We have divided by X minus 8, except we just used the solution instead of the factor. So that means we have taken 1 degree out of this thing. That's why all of these are going to be 1 less degree than it was originally. So this will now be an X squared term, that'll be an X term, that'll be the constant or the Y-intercept, and we may or may not have a remainder. Well, actually we do. So your answer in this problem would be degree squared minus 5x plus 6 plus remainder of -1 over negative x minus 8. Okay, and that's how you do synthetic. Let me get out of here. Go have a nice weekend. Maybe I'll bring some Halloween candy to make up for all those times I've kept you late. Anybody like candy corn? Yay, nay? That's good. You can start eating it. It's hard to stop for me. Actually, we would have finished perfectly on time if I hadn't have done the test stuff. Why would you ask that? You got to give it on the last. Yeah, and then spoil. That's right. Don't count on it.
So much.
Hey, we still got another week of new stuff to go.
Okay.
Just a simple word of encouragement.
Come on.
Thank you.